Hi there, my name is Thomas Jarlev and I'm the founder of CX Planner. CX Planner is a commissioning management software used to streamline and optimize your commissioning process. CX Planner is specialized in documentation, testing and verification of construction projects. The team behind CX Planner is all commissioning professionals, and all our knowledge has been put into CX Planner so it's practical and easy to use. I would like to show you how CX Planner can optimize your commissioning process and streamline your workflows on your construction projects. Book a meeting with me. I'm looking forward to seeing you.
Good afternoon, everyone. My name is Sam Schwartz, and I'll be your moderator today. Welcome to the ABC Commissioning Group's ACG Essential Commissioning Webinar Series. This is our third year hosting a webinar every month through July through December, and we're excited to provide a fresh new lineup of topics related to the commissioning process. And special thanks to CX Planner for sponsoring this particular session. I am going to cover just a few housekeeping notes before we run into things. The presenter today will be taking questions at any time, so we encourage you to submit them through the Q&A button throughout the presentation. If you happen to be experiencing any technical issues during the webinar, please use the chat function to inform the panelists, and we will assist you. This presentation is being recorded, and we will send out a recording for availability within 1 week. In terms of continuing education credit, everyone in attendance for the full webinar will receive a certificate of attendance sent to their emails within 24 hours. And for those certified CXAs or EMPs in the audience today, your CEUs will automatically be uploaded to your respective portals for you. So today's webinar topic is passive cooling and natural ventilation design, construction, commissioning, and operations with John Herboth. He is a senior commissioning engineer at Affiliated Engineers Incorporated. He has started his commissioning career in late 2007 with Northwest Engineering Service Incorporated, and he's been working with project teams to commissioning buildings for over 15 years now. He currently serves as the Northwest chapter president of the Building Commissioning Association and believes that sharing project successes, failures, and best practices is a professional duty. And so happy to have him here with us. And for everyone attending, thank you for joining us. And with that, I'm going to hand it off to John to get us started today. John, take it away.
Thanks, Sam. All right, everybody see my screen? Let's get rolling. Appreciate the introduction. Just as an FYI here, you're only an expert when you're around other people that aren't familiar with systems, and there's always more to learn. So I really enjoy learning and teaching at the same time. So your questions will help improve this type of presentation and my knowledge as well. It goes both ways. I just wanted to give a few shout outs to some fellow contributors. I first did a presentation on this back in 2019 with Ruhan, Glenn, and Matt for the BCA. And then since I've adapted this and will continue to adapt this as long as it's one of my passions. So I want to give a thanks to them. This is an AIA registered presentation, so I won't be selling anything. This is informative. And if you have any questions, feel free to ask or follow up after the presentation. And for the course, we're going to talk a lot about passive cooling and natural ventilation systems. They sort of go together. What type of environments they've been in historically and what they're being used for now, and how they're trying to be adapted for reducing energy use. It's not a new design concept. You know, before HVAC systems, this is how you cooled buildings. You know, geometrically drawing air in and cooling system down, places where you don't have electricity or don't want to use electricity. This is something that strategies that are used across the world. So, but try to integrate it with new building systems and our current construction methods, there can be some challenges. So we'll talk about it. Along the way, I hope that you learn about these systems, some of the concepts, how construction impacts them, what are some best practices for the different phases of a project, from the design, construction, operations, and commissioning, which is throughout the process, as well as some ways to identify some of the concerns that you'll be presented with if you work with these systems in different intervals, for parts of the project, and then some of the responsibilities and implications, that on the operational side. So, these buildings have to be maintained for the rest of their life. So there's two parts to a project, the project itself, and then when the project's live. And so we'll talk about that as well. All right, so here is, let's see, this is one of our, some of the concepts that we have here. We, in passive and natural ventilation systems, we have chilled beams are often used for sort of in space heating and cooling for adding to the room when you're using natural ventilation. So instead of forced HVAC systems, you're going to be using radiant slabs or chilled beams, heated and chilled or above head heating systems. A lot of ceiling fans are used regularly to circulate that air as well in a space. Certain new projects, especially some of the living learning labs, have phase change materials. You don't see that too often, but it is a component, as well as PV. Whenever we're talking high performing buildings, that are trying to achieve net zero, you want to integrate a lot of these systems so that your overall EUI can be dropped way down, and the generation that you have on site can overcome that building energy use. And the whole purpose of all these two systems are decreased mechanical hours. Not only can you decrease mechanical hours, but then occasionally you can also start downsizing your mechanical systems. Now, we live in changing climate where we have more hot days or more extreme weather. And so there's a lot of other considerations that have to go into these types of systems now, such as, wildfires. How do we close these systems up, when we have poor air conditions outside? So we'll talk about that. So I'm going to go into a first project as a good example. I like to use projects as real examples because it tells the story and it's easier to learn from stories. So this first project was my first natural ventilation and passive cooling project. This was for a higher education remote site in my area. I live in Portland, Oregon. And I was actually brought in post-project for a recommissioning. Now, there was also other things going on besides some issues with the HVAC systems and occupant comfort. This project also had some construction issues with the envelope. So we'll talk a little bit, we'll focus mostly on the passive cooling and the natural ventilation system. Now, the building here, though, is a building that used PV because it's net zero. We used electric heat pump, that could do heating and cooling on site. It was a multi-stack unit. And then we had dampers at the floor level, and they were coming in and then through a ducted and non-ducted shafts up in the ceilings, and then out turbine ventilators at the top of the building. So it was inducing draft by having both a height differential and a chimney effect at the same time, where the hotter the air, less dense, drives it up, and you can induce draft. This is one of the really big considerations anytime you want to use passive cooling, because it's not just like you're opening windows and having all the windows open in a room. How does the air circulate through the room to provide a temperature drop, a felt temperature drop due to convection, so that you can get the temperature down what you feel is the temperature. Anyways, it also had some solar and daylighting, and then it had some sequences to take advantage of the building automation system integration. Anyways, so this slide here is just to show you how a lot of these buildings are using models to take a look at what the code baseline is on one side of the screen, versus what the model for this building is. Because anytime you're trying to achieve a high performing building that's net zero, trying to aspire to be net zero, you really have to start digging into the individual loads on the building and start breaking down how can we reduce these loads. And as you can see, with all these different systems in place, you're saving over 50% from the code baseline. Now, this is a while ago. So this project is probably, I think, designed in like 2010. So this first project's a little bit older, but as we start getting to these other projects I'm going to talk about, we'll start talking about code that's actually projecting for the future. So here is a diagram of the ducted shafts. On your left, you're going through, and you can see where sometimes it's ducted, and sometimes in the middle, or diagram number 4, where it is not ducted. And the components of this at the top are, you're going to have these turbine ventilators. Now these can operate without power, and then they also motorized as well to induce draft mechanically. And then you have dampers to try to isolate the airflow when you don't want to have draft through your room. And the same thing in the space, they used double sets of dampers facing opposite directions. So blades, one will go down and one would go up to try to reduce draft. And so there are double deep dampers to try to not have unintended air drafts, because that is a killer when it comes to occupant comfort. Bringing in too cold of air when you don't want it, or too hot of air when you don't want it, is not a good thing. And then usually for all these types of systems, there is some level of occupant override to stop the system from operating. Say that there's somebody mowing outside and creating a lot of dust or noise. You want to have ability to stop the system from automatically opening and closing. And then user controls. This project had a few too many in my mind, post fact. But the more controls that you have, the more that you risk that you can have user error. So there's got to be a happy medium. You don't want everything fully automated, because then you rely completely on the automation system and an operator to fix something if something goes wrong. But you want to give the user also the ability to control their environment, because people can feel much more comfortable in a hotter or colder environment if they have control of that environment. So it allows you a little bit more wiggle room on the temperature range you can have in a space. Now, here's a picture of the actual double damper sets here. And you can see there's 2 wide and then 2 deep. And this had some exterior angle iron. So the only way to, so it was installed from the interior. And then the exterior had a louver set as well, sort of acting as a rain screen. Now, there was also casement around. You can see in the bottom corner, you had a grill and then some casework on top of it. This really made it a little bit difficult to access and remedy any situations in the long term. So when we were brought in, my firm was, they had already had multiple issues, and unintended drafts was one, serviceability was another one. And so we started to take a look at that, and I'll talk more about that in a few seconds. But if you can see already, when you there's only one motor for these 2 sets, for each of these 2 sets. And that can cause its own problems, because when you add more linkages in, there's going to be play. And when you have play with dampers, you have gaps. So this is what you start taking a look when you have a radiant floor slab. You can see that it's nice and warm there, but you can literally see on the damper sections, especially that second damper set, it's cold. That's 53 degrees air that was able to come in. And I don't know about you, but like 53 degrees on the back of your neck, just like from a diffuser dropping it down on you, or 53 degrees at your leg level, it's not comfortable, not at all. So they were having a lot of complaints. And what ends up happening was that you ended up having the maintenance team, who I think it was about a 40-minute drive from their main office where the facilities meet, this is a remote site, they had to literally cardboard and tape off these damper sets that were acting like this. And so anytime you start having to modify systems post-project, you really don't get a lot of good buy-in from the operations team to maintain it. And so this also dragged into other issues. Just like when at the end of a project, you don't want a red blinking light on a brand new system and you hand it over to somebody, it can tend to lack of ownership is what I usually term that, because you start risking that when you don't have a system that operates well. And I mean, that's why I have a job, is to try to verify systems work correctly prior to handover. Doesn't always happen at that point. Sometimes you're there post fact and the risk factor goes up. But there was other problems too. During the summer, the HVAC system could not cool the building. And that is also from unintended air leaks. The leakier your envelope is, and you're going to have heat load coming in from the exterior unintentionally. And the HVAC system wasn't sized for it. Now, we found out actually later on too, that this is a heat pump chiller. This could have done slab cooling, but it wasn't tested on the initial commissioning effort and the initial project level. But all the components there were there for that. When we also started digging into the energy use, they were very close to net zero, even with all these issues. So, I mean, we're talking, 15% away from getting to net zero. And so it was, all the math was there. It can make it, but we just had to dial in all these little issues and start finding ways to better seal the building up, get better performance out of these dampers, and then start editing strategies to utilize the system so that it would provide comfort during all these peak times. So during the recommissioning effort, we took it into sort of three components. How do we physically improve this? How do we do some controls changes? And then how do we train the staff and retrain them on the system after all these changes to get that buy-in, and also to make sure to get its long-term success. So we ended up doing full device checkouts, doing condition assessments on equipment, going through and adding energy meters because they didn't have them on every single system. So we needed a little bit more granular information from the subsystems. So we added those. And then we started obviously taking the worst damper sets and replacing them. We didn't have the funds to do every single damper set the way we wanted them to, but we went through and did all the worst ones. And then for any of the other ones, we took and added extra gasket material to start reducing that air leakage. We also went through and did some turbine, the controls revisions. So instead of everything, it was operating just like on a PID loop, and it acted pretty fast for opening and closing these dampers. So instead, what we ended up doing was we started taking in the smaller bites and staging it. So like 0 to 25% damper position as stage 1, 25 to 50 as stage 2, 50 to 75 as stage 3, 75 to 100 as stage 4. So we started slowing down that PID and giving it stop points to try to give opportunities both for the occupants, if they wanted to take control, they could, or to react to the rising temperature in the room in a little bit more of a measured fashion. The second really cool thing about this is 2000, gosh, I want to say 14 is when I was doing the recommissioning on this project. It was finally available to start pulling in weather forecasting data. So it was a simple module that you could add for the automation system components. And instead of having to make your own weather station on site and do additional programming, you can just pull it from the web. So we started pulling in forecasting the next 3 to 5 days in advance. And then we went through and proved that the heat pump chiller could do slab cooling. We had dew point avoidance because we had humidity temperatures, like all the components were there to avoid condensation, unintentional condensation on the slab. And then we started playing with how long would it take to go from slab heating to slab cooling. And we figured out that we needed at least like a 2-day advance notice of a hot day. So what we did was, if we put into the programming, if we saw that there was going to be 3 consecutive hot days above 80, 85 degrees, we were starting to hone in on what was going to work. Then we went to slab cooling. So we switched over. Prior to that, I think we ended up choosing something like 36 hours in advance to do swap over. So by the time that we hit the hot afternoon, that we were down to like a 60-degree slab. I think we were dropping it down to 57, 56. I think we gave ourselves a +2 degrees from the worst dew point temperature in one of the rooms. And it worked. Like, this was so surprising. Luckily, I was doing recommissioning during the summer, and we were able to do this and really spend the time fine-tuning it. You find with a lot of these high-performing buildings and net zero buildings that they need a lot more tuning. And the more adjustable points that you have in the sequences, the more direction you need from technical people to be able to adjust it. Relying on the operators to make all those adjustments themselves sets you up for a higher risk of it not being adjusted in a way that's going to work well year round. And then another cool thing is, with this, I led my first training session. I found that after all this recommissioning, I was the most knowledgeable person to train the staff. And it was one of those fun experiences, being in a room full of maintenance guys that, are 20 years older than I am, anywhere from 10 to 20, 25 years older than I am. But it really hit home when you could show them all the work that you put into it, sit up there with, say, like the controls rep, the heat pump manufacturer, and really go through and hit it home and how these systems are connected and how important it is to maintain certain aspects of it for its success. And then get less occupant complaints and less phone calls, which, that perks people's ears up all the time. So you can see here, we went down to 1 damper per actuator, and we went with the lowest leakage class. This was definitely one of the things where you want to buy high quality components, and even started improving what fasteners were used to get to these components, because some of the clip-on for fasteners, the backs of them aren't very good, and they just dropped out. We also added a lot more foam insulation now too. We found it was really leaky around the frame as well. So there went a lot of work to try to improve the envelope insulation and reduce leakage. And it really, really made a difference. And then here's another thing. You can't prepare for everything. Sometimes you have bird's nests inside turbine ventilators. And they'll get in there and they'll make a nest, and it's an echo chamber all the way down to the classroom. And so bird screens are very important to think about in the design rather than post-fact. This ended up unbalancing that turbine ventilator, so we had to do some field balancing to make sure that it wouldn't spin and create a wobble and noise. We started putting in some O&M procedures as well, from seasonal damper leakage checks using a thermal IR camera, and then posted new training directions in the classrooms, with lots of pictures, and then making sure that we assisted in responding to complaints and logging all those complaints that first year afterwards, after the recommissioning, and assisting the operations team to make sure there was no other source issues we should be looking at. So it always takes more time. And I found that with a lot of these projects, not only on the tuning side, but also on the assist side with the operations team. And so now we talk about it as ongoing commissioning for projects, and that's probably what these type of projects require, regardless, because of the amount of tuning it needs and the support they need for operations staff. Unless you have an onboard commissioning provider with that owner, then you might be able to get away with it. So I'll revise here, rehash my lessons learned there. The simpler the user controls, the better. Include as much automation assist functions for operators. Select high performing components and that are durable and that can be taken apart and easily accessed and then re-put back together. Accessibility, maintainability is a top priority for the long-term success. We don't want these systems to fall into disrepair after just a few years. Lasting 20, 30 years is really important. The only way to do that, they need to be accessible, replaceable, and maintainable. And then enclosure inspections, because we have sort of a cross in the road between architectural mechanical components, that you really, really need to have enclosure inspections as a value add, and it really reduces project risk. High performance buildings trainings should involve a designer and maybe the CX provider for the overall system training, because you have all these individual training sessions, mechanical, electrical, plumbing, controls. And honestly, some of these are where systems sort of converge and go together, and having an overall understanding from the mechanical engineer record about the system intent, how it's supposed to function, along with the startup rep or the manufacturer rep doing training, and then a commissioning provider there saying how it functions, how we vetted the system, really gets that team buy-in from the staff and from the O&M facility guys and gals. And it really, really improves your chances of success. And then you become a resource too for that team. Might not be always the best thing when you get all the phone calls, but I don't mind it for now until my inbox gets full. Let's see. So we're going to move on to my next, it's a triple project together, 3 sort of identical schools that use passive cooling in an elementary school. This is the one where Ruhan was the engineer record from PAE, and he did a really good job of going through and considering the different design aspects as they took a look at how we're going to meet the architecture 2030 target. Because you have on one side of this, you have the baseline, code baseline, and then you have incremental steps to get to that architectural 2030 target, and not just having, how can you get there? Because you have to do reductions everywhere. So what they first started taking a look at was climate data. So you have this window where passive cooling is optimal to keep your indoor temperatures within their range, and that's typically somewhere when your outside air temperatures are between 60 and it's about 75 degrees, at the most, is where you can typically do it. And so you can see there was only about 36% of the year in Portland, Oregon, where you had hours that could support non-mechanical cooling using passive cooling methods. But if you take a look and if you do a super envelope and you start looking at R40 and R50 values in your walls and start being selective on how much window area you have, you can start massively increasing that passive cooling window range. And so you take a look, and because of the envelope, you can start really utilizing temperatures that are way beyond what you would think you would use, but you have to have strategies to avoid bringing in cold air that's too cold or too hot of air. So, I don't think you're going to necessarily bring in 45-degree air into a space or even 80-degree air in space. But because of your envelope and your ability to keep it warm in space, and you're using, say, in-space heating or cooling methods, then you could bring in that air that might be uncomfortable by itself. So his system that the PAE team put together, utilized operable windows instead of dampers. You had an in-space green light indicator for the temperature range was within, a good range, and then a thermostat for individual heat pumps in the spaces. So you had in-space heating and cooling, which could be matched with that outside air to keep the temperatures in those far ranges from being too hot or too cold. but it wouldn't rely solely on the HVAC system. Now you also had some other automation controls to eliminate simultaneous heating and cooling. You also had still turbine ventilators at the top of a shaft with dampers set to prevent an air route out when you don't want it. And then also access above the roof into a doghouse. So this was a much simpler system. You just had your thermostat on the wall and then an LED sensor versus, 8 different options from lighting to dampers to ceiling fans. So in this system, it had no ceiling fan because you had the ceiling mounted heat pump. So here's a little bit of an energy use breakdown. So whenever you have to do these calculations on the design side, you really start taking into the meat. You have 30% here for space heating, and then you start breaking down what you're using that heating for, and you can start taking a look at where can we start cutting stuff, or what systems can we use to reduce our total energy use and mechanical hours. As you can see, window heating, the more window area you have, the more mechanical heating and cooling you're going to need. Windows, as good a U value as you can get, it makes you can have R50 walls, but if you have 50 wall to window area or more window area, your overall envelope is going to suffer greatly. So your high-rise systems aren't going to be able to use this if you have an all-glass facade. Here's a fun one. So this project, though, had some turbine ventilators. And this system here, as you can see, there was no bird screen on the outside. It was actually on the roof level of this doghouse. And the really important part for these turbine ventilators is not only can you get free draft induction from the wind outside, but then you can do the powered version as well if you need to increase the airflow. One of that big consideration I was talking about earlier was how do you induce draft? You can put all this effort into a system like this, and if you don't get the draft right, it doesn't work. You can put all this effort into a natural ventilation system, but if you don't shape like your chimney, if it's not shaped right, it's not going to work. So this was another calculation here by his team on, for the roof turbines and how they were going to improve rejecting heat out of the building. And another important part here is where do you apply this? Whether it's an office building, classroom, sort of the office spaces, your gyms, they made sure to take a look and only apply passive heating and cooling into the areas and natural ventilation into the areas where it's going to be the most productive. And that was in the classroom setting. When you're with just a small office area with one person in each cube area or individual office, it doesn't work very well. And on the first project we showed, we ran into that. A lot of the office areas with just one person in it, that having that much airflow into a small space to try to give occupant comfort, it didn't work very well. So it really works best in a larger office area, an open office area, and individual rooms, not so much. Especially if you're trying to have phone calls and stuff like that. You find it to be more of a nuisance sometimes. It can work well in gyms, but it's another area where the amount of air circulation that would have to happen is pretty high. And they already do a pretty good job with the height of the ceiling to allowing a good circulation, sometimes with ceiling fans already. Here's a few other sort of metrics that they went through to try to see how they could optimize some of the functions that you can automate. Night flush ends up being a huge one. So for night flush, it's really about rejecting all the heat, the thermal mass, and bringing that temperature down prior to the next day. So when you have multiple hot days in a row, if that nighttime temperature doesn't drop down, a lot of these strategies won't work. But if you can start rejecting some of that heat by drawing out the thermal buildup from the day, then you can set yourself up for a better situation the next day. So say your temperature dropped, say you had a high of 90 degrees, but you drop down here in Portland, often it'll drop down below 70. So if you can reject the majority of that the heat from the previous day and not let it roll into the next day, then you won't get out of control. So they went through a few iterations on, how much overhang they should have to try to prevent that heat load from really that thermal mass from heating up too much on the surfaces around the classrooms. So also talking about different ways to really bring that temperature down. Let's see. So here's that detail on that roof turbine for that doghouse, and you can see that blue line. That's the integrated bird screen. So they learned their lessons. Now I hope a bird doesn't. I don't know if they've ever had a bird build on top of that screen, but that could be an issue there too. I bet you'd be uncomfortable though with that turbine ventilator going, but it might be messy to clean up. But here's the aspect of where mechanical and architectural comes in, and why it's so important to have a good architect or building envelope consultant really help flush out these details, because a flat 2D image like this looks like, oh, this is not too bad. This will work really well. But when you actually construct everything, the 3D aspects and all the geometries of this building, it became really important to also have somebody there during construction to make edits and explain to the contractors how to best layer all these components. I have a passion for building envelopes. I still consider myself a student and not much of a teacher on this side yet. But I also did building envelope testing for almost a decade as a service provider at my previous firm. So it's really hard for me when you take a look at this here and not think of all the negative ways that if you don't detail it out, the outcomes that can happen. So getting these type of comments in here, I think this was RWDI that did all of these comments on this project, and they did a really good job of getting things like even the surface conditions of what the shaft was going to be like, where the fasteners are going to be so that you can access them from the exterior. So this doghouse was accessible by just walking into it through an access door. So you want to have all the fasteners on the outside so that you can pull the damper assembly out. And then if you needed to replace it or access the shaft, go in there. A thing that I've learned too here is that these shafts, whether it's even 1 story, 2 stories, 1.5 to the ceiling down below, that having a D-ring up at the top is really important so that you could do a service rope and go inspect it, or having even a rope there already with some cleats at the bottom, because accessing that shaft ends up being really important. The more stories you have, the more important it is to be able to inspect that shaft and get it done right the first time, because once they close it up, you're going to have a really hard time fixing any problems in the long term. And if you don't put a D-ring in there, an ability to have somebody go in there and inspect or repair something, the long term, you're going to potentially run into problems. Let's see. Sam, do we have any questions on this one right here?
So one just came in. What are the advantages and disadvantages of using the turbine ventilator?
Well, the disadvantages for some of these is that if you don't have a good damper set to isolate it, you can have unintended negative draw on the outside and pulling air through unintentional openings. So that's a negative. So you have to really make sure that you can isolate its operation. In this picture, there's actually a gap to allow water out of the drip pan that's underneath the turbine ventilator. So this turbine ventilator could spin by itself and not induce a large negative pressure on that damper set. So that's one of the negatives that can happen that I've seen, is that if you can't allow a turbine ventilator to operate by itself, that you can have an unintended consequence. But the positive is that you can get free, it can spin freely. So with the wind, you can get free induced draft as well. So it's an energy saver. And on top of that, inducing draft mechanically is a huge benefit in case you aren't getting a natural induced draft due to shape and no wind available to spin that turbine. So, I think of it as a fail-safe to make sure that your system works, and also can improve its operation and really get a good amount of air volume coming in from the space and out the chimney or shaft that you have. So I think overall it's a really big benefit, and some of all the disadvantages you can mitigate, except for the birds one. I don't know if we've quite solved the best way to get out there until they put turbine ventilators with some integrated mesh screens. Anything else?
No, we're in the clear for now.
All right, I'll keep going. So this is one where if anybody that's on the line, hey, actually, Sim, can we do our first poll question so I can understand who's in our audience? Excellent. So while people are answering that survey, so I understand who's in my audience, the building envelope side for these shafts becomes really important, and the damper sets or whatever way that they're trying to bring air in and out of the building, because you are basically having an intentional opening. But by having an intentional opening, you can have a lot of unintentional air leakage into a building. And as these energy codes get a lot tighter and include a lot more air barrier testing, like in the state of Washington, the pass-fail rate, I think, has dropped now from 0.4 CFM per square feet to, I think it was like 0.25. But as these air leakage values come down and trying to get tighter and tighter envelopes, you're introducing another penetration into the system. And so it also becomes important what type of surface conditions we have on these shafts, how do we isolate them, and we really want to make sure that these are thought out, both on the face value of it, what's supposed to be there, how it's going to be accessed, and then making sure that it gets done. So it looks like we have most of our answer from that first poll question. Mostly commissioning providers, 71%, few engineers up at 17%, no architects. A few owners, some contractors, no facility operators, and a few others. Thank you. So for the commissioning providers, that's what I do every single day. This is really an opportunity for you guys to ask a lot of the good questions and add value to the system that's being proposed. And for all the engineers that are on here, there's always an opportunity to get an outside perspective on making sure that the little details also get thought about and included in the project specifications and drawings, because we want to make sure that your guys and gals design intent gets brought to the front. And when we get contractor involvement, we don't build this every day. So understanding how this stuff can get built and the sequence of it getting built, a lot of times these shafts get built first. And so you want to make sure, and that's sometimes not even before any of the MEP systems are in. So you want to make sure that you have some QA, QC, some inspections on these, make sure that they're all done. And maybe the commissioning provider's not there at that time yet. But it is really important that we do get these inspected. There's a lot of opportunities for air and water intrusion in these shafts. And if there's gaps in between the floors, it's not going to work very well. Also, Pandex, get them sealed, all the edges sealed. Just becomes a great air conduit in and out of the building, especially in between floors if those aren't sealed up well. All right, we'll keep going. There we go. During this project, there was some fun construction revision. During this project on one of the sites of the 3 schools, during staging, one of the turbine ventilators, which is parabolic and very shiny, was staged in a position where the sun was able to catch it, and one of these doghouses went down in flames I wouldn't say the delight of anybody, but it was one of those sad sights where unintended staging of a component, took out a lot of people's hard work. Now, you can't predict some of these type of stuffs, and who knew that selecting what type of finish on the inside or on these metal components, because normally it's domed, and so you wouldn't worry about it creating a focus point, but because it was staged upside down or to the left, right, it ended up being basically a magnifying glass. So who knew that selecting a matte finish would have been important? But in the future, for anybody, try to avoid super shiny surfaces that can cause hot spots on these type of turbine ventilators. It's a good idea. Mounting all the actuators externally so they're accessible. They had made a lot of revisions to the access doors, make sure that you could get in and out easily. There were some drainage concerns, so they played with the drip pan underneath everything and how the water was going to get out. And then, like I said, the matte finish. So here it is. Here's that actuator, but if you can look at it, it's not easily in a position to slide off. But later on, they made some edits to make sure that that was easily replaceable because motors fail. They started looking also into an auto reset on the temperatures, as well as when stuff turns on and off, making stuff adjustable. They initially had a sequence that disable the fan coil unit in the space, the heat pump in the ceiling, based on when the NAT vent sequence was active. And originally, if two classrooms in that pod were using their NAT vent sequences, they would disable the cooling for the entire area. And when we first saw that sequence, we understood why it was there, to try to promote as a group the use of this system, but ended up later that they removed that. So operations and maintenance, this project, luckily we had the PAE team help with some of the training. And this was one where it was a really fun one to do with the maintenance team, where they could understand how much effort went into the system. And it was really effective. We also took a look at making sure that there was, we implemented the lessons learned from the last project of inspecting the dampers with a thermal IR camera, also going into the space and looking at the ceiling for the grill in the space as another location where you could see if it was inducing a draft unintentionally and around all the operable windows. And so it's great, handbag tool these days now with thermal IR cameras. You don't need the super expensive ones to spot leaks because you're not putting a certified report together. But it's a great way, and maybe even, that's definitely something that needs to be in the toolbox for any facility team that has these types of systems. I talked a little bit about some post-occupancy challenges and changes. The school district had an agreement with the staff to make sure that temperatures stayed within a very specific range. And so I think the high end ended up being only 74 degrees. So that did limit the overall effectiveness of this system because of that union agreement. So they had to make some changes on the set points, and it definitely took the top end temperatures out of the possibility for the use of this system. And then they eliminated also that group mentality of if more than two rooms were using natural ventilation, that they would kill the mechanical cooling. So lessons learned, talked a little bit along the way here, owner and staff and design and construction team buy-in improves outcomes. I mean, the details really matter in the drawings, and putting a lot of thought there on the constructability, and it will lead to less field mistakes. Team experience is really important with these systems. So if you have a project that has these types of systems, then it's really important that somebody has experience with them to bring some of these lessons forward or utilize a resource that does have that experience. And then you can't always anticipate every failure. fires happen, and hopefully it doesn't happen on your next project. And every opportunity you can to learn and pass that actual knowledge to others is a good opportunity, regardless of what your background is. And then before we get into the last little short project, do we have any short questions, Sam?
Yeah. Is this system workable in high temperature and high humid locations like Middle East and Gulf regions?
Unfortunately, the climate is so important for location determination, whether these will work. I mean, I live in the Pacific Northwest, so this is a great region where you have more moderate temperatures for the majority of the year. But the higher extremes that you have, whether you're in any desert areas or any mountainous areas, the more likely you're not going to be able to use this system, and your window for when you can gets narrower and narrow. So yes, you can use these systems there, but your opportunities are going to be a lot more confined. And then if we have any other ones, we'll probably save them for the end so I can get through this last little set.
Sounds good.
Okay. So this last one is not constructed yet. I think they might be in construction now, but this is another natural ventilation passive cooling for a higher education site, but this is a design and fabrication center. And here is some cool imagery here, where they really did take a look on what induces draft. And they did a chimney effect as well as a modeling of the shape of the building. And then what's interesting on that sloped part of the roof right before the discharge area, that's actually going to be clear glazing. And so that it would even heat up that chimney area and inducing more draft the hotter it got. So not only would it rely on the stack effect because it's a 4-story building, but it would also really promote that temperature draw chimney effect. And so here, you take a look at your model. You have low intakes, damper assemblies with glazing to encourage that chimney effect, and then a really high wall relief. But what you see here, and I started commenting with the team that was designing this, how do we access that upper high wall relief? How do we replace it? And making sure that we don't create inaccessible components because they will fail. And especially if they're motorized, that motor will fail. Here is a control drawing, and this was a unique setup that I hadn't seen before. On the natural ventilation damper in the corner there, they also had heating water to do heating through the natural ventilation. So you then could now use it basically like it's a cabinet heater, but instead of circulating from the interior, it's pulling all outside air. So this is a great way to utilize it's basically a direct outside air into the space, but with heating there, so you could have winter conditions and you could still be utilizing your natural ventilation system. There's also opportunities here where you could have a temperature sensor, making sure that we didn't have unintended leakage by using that supply air temperature sensor, and say that the valve was closed. You can start doing some fun things there, and I'm looking forward to seeing how this is going to work in the field and what to learn from it. There was one aspect of this I didn't like, though. I took a look at the detail that they had for the architectural, and this is what I was talking about, where you have a need for sort of a mixed architectural mechanical detail, where it shows how this is going to be placed and constructed. And if you look there, the damper set is after the heating coil. Okay, how's that heating coil going to be serviced? How can it be replaced? How is that damper assembly going to be accessed and replaced? Now you have to think of, okay, with this heating coil here, can that be removed? And if it can't, then now I have to be able to take that rain screen on the exterior out to be accessible from the outside. So you gotta start taking a look at how can I get at these parts, and how can I replace them? How can I service them? And this diagram threw up a lot of red flags for me. And with that, I'm going to end and open it up to Q&A. This is one of my favorite pictures, by the way, and this is how I end most of my presentations. That's I having a picnic at the research station down in Antarctica. So,
Is that you in the picture?
no, I don't do well in cold.
All right, thank you so much, John. So we have about a few questions lined up, and anyone else in the audience, we still have a few more minutes, about 5 more minutes to go through the Q&A, so feel free to plug them in. So John, was the Denglass board utilized all the way in the vertical ventilation shaft, or just the portion between the operable damper and turbine ventilator?
Denglass was the interior for that entire shaft. And then, so they're using what's typically an outside component, sheathing component, and they use that to line the interior of that shaft because guess what? It was essentially the outside of the building coming into the building. So yeah, it was Denglass all the way down.
Great, thank you. Next question. Passive systems only work in designated weather areas. Are these defined by ASHRAE or the energy codes?
Can you repeat that? Let's see. Passive.
Passive. Oh, you see it?
Yeah, I can see it now. So yeah, you're gonna have weather areas defined by your ASHRAE categories that it's going to be more conducive to being a viable system. Now, it doesn't only work there. Now, I was saying earlier today that you're going to have a much more narrow opportunity. And then there's going to be areas where you just don't want to do it. Your high humidity areas are going to be the ones where you want to avoid using as much unconditioned outside air, or you're going to have to implement other strategies to try to pull moisture out of that air prior to introducing it into your space. So yes, it doesn't only work in designated weather areas but it will work anywhere, but you're just going to have to put more and more effort in. And then sometimes it won't make financial or short-term or long-term viability.
Okay, next question, and here's a good one. Are there concerns about drawing in outdoor air pollutants?
Yes. Now, we are on the West Coast, and even now when you're in the Northeast or any of the North with Canadian fires, California fires, I mean, there are so many different outdoor bad air conditions possible in so many different places, whether it's pollution from cars, from motors, or from fires. And so this ends up being something that needs to be tied now to air quality stations. And that is an important automation control to close these systems and not make them to automatically do it and utilize local air quality station, which are now available, and you can pull that information. I think even some of the controls programs have that as a module now that makes it really cheap to integrate into your building automation system. And so not only are you now doing weather forecasting, you're doing air quality integration into your routines to, hey, if our air quality is above, especially if the 100 level, where it's hazardous to health, we do not open up these systems. And a lot of these systems don't have filters on them. You're not putting filters on your operable windows. And for the most part, you're not putting filters on these outside air louvers. Now, can that be a consideration? Yes, you could. On that last example, you could put a filter bank in there. If you were to bring this out, you could put it on the discharge side. I think on this one right here, it looks like more that you could put a filter box. So you just have to start considering what's happening in your area, and maybe filtration is one of them. But yeah, the concern is there. You have to start addressing it.
Great, thank you. 3 more questions. John, do you have time for a couple more questions?
I do.
Perfect.
Let's keep going.
Okay. Next one, also great. I like the idea of natural ventilation, but controlling the pressurization inside the building with the natural ventilation is harder and more complicated. How can you make sure that pressure in the building is controlled properly?
So when you're using natural ventilation, you're creating a negative pressure on the interior. And so that's sort of contrary to what you normally want. for most buildings, you want to have a slightly pressurized building to not have unintended infiltration. So you got to understand that with a lot of these rooms, we're thinking of more like pods. So as, say, a classroom opens up, or a designated like large open office space area, or a different type of area that uses natural ventilation, you're going to have a depressurized space as part of the building. And that is something where if you have a building automation routine for your air handlers on a roof that use a space pressurization sensor, that you're going to want to either isolate that from that individual room or all the rooms that can do that, or when NatVent sequences are enabled and operational, that you disable that building pressure control, or don't allow it to ramp up a fan past a certain point. So you do have to put bounds on those equipment and controls when it comes to pressurization control. So if you're talking, say, like a lab space that might use natural ventilation system for, say, their office areas, their desks and everything like that, or you might bring it in as sort of your makeup air system for the exhaust, you do have to consider pressurization, and maybe it's not a great idea if you have something that's sensitive, or you need to isolate it. You can't make sure. So if you're going to have to add sensors to show what your pressure is of that individual space that has natural vent sequences, and the say the general office area or building pressurization for that rooftop unit. So you got to start having either more sensors and more thought on how you're going to do it.
Hey, thank you, John. Next question is, how important are reversible prop fans for summer winter operation for energy and comfort?
Let's see. Can I get a little bit more information on reversible prop fans? So
we can come back to that question.
I'd like a little bit more information in like what is it being used for. So are we talking about in the space just for circulation, or are we talking actually part of the natural ventilation system?
They said statification purposes.
So a lot of these spaces use ceiling fans to try to promote circulation, especially the higher ceilings that you have, especially if you're in an atrium space that is using this. And so regardless of whether it has a natural ventilation component to it, I promote having reversible ceiling fans and any of those prop fans that are conducting, whether the air is coming down the sides or being drawn up the center. So it's important if they're going to be used throughout the year rather than just during the summer. So having reversible so you can do it summer and winter beneficial is a plus.
And final question for today, what coil freeze protection is considered for those HW coils at intake louvers?
I actually didn't get to that one on that project. I didn't take a look at their mechanical systems. I imagine if you have anything that's going to be exposed to outside air, just like a rooftop unit, that you're going to have glycol in that system if you're in a freeze climate. And then if you're in a really cold temperate climate, then you're going to have to think about what type of what type of liquid you're using in your system and whether that has to go up. So typically you have coils. I prefer not only using glycol just as the standard means and methods here, but also having a hardwired freeze stat would be important as well. I've had freeze coils frozen on multiple projects. Those stick with you for a long time. Hardwired freeze stat and some sort of glycol protection is definitely a plus because the cost of replacing one it gets astronomical when water gets everywhere.
Well, thank you for the insight. John, thank you so much for this entire presentation and taking your time today to come on and speak with ACG.
Of course, Sam. And if anybody has any questions after this, feel free to forward them to me, Sam and Sim, and then I will answer them and get back to people.
Absolutely. Do you mind advancing the slide?
Yes.
So as an outro, we have this series going on through December, one webinar each month, and the next webinar is going to get into integrated systems testing with Mark Gelfo, who's a great presenter, and we hope to see you there. Please mark your calendars for August 10th at 2 p.m. Eastern, and have a great day and see you next time. Bye now.
Thanks, everyone.